Hi, today we are going to look at OpenMP. OpenMP is different from what we've been doing before, which is MPI, in that OpenMP is meant to run on one computer, which has shared memory, whereas MPI is designed for use on many computers that are networked together and so do not have shared memory. That's why MPI it has to do everything by passing messages from one process to another. OpenMP does not have to do that. OpenMP, it's all on one computer, so all the processors can see the same memory chips. And because they can see the same memory chips, they can access the memory directly. This makes things better in a lot of ways, but also more dangerous in other ways, which we will go into. So OpenMP is an API used for multi-threaded shared memory parallelization. As I mentioned before, that it's all shared memory. It's on the same computer, so everything is shared. And the way it does that is it takes a standard C or C++ program and adds certain special compiler directives. And these compiler directives then will tell the compiler that it's going to do some sort of parallelization. And it also ties into certain runtime library routines, which then lets it do those parallelizations. It also uses some environment variables that tell it what it's going to do. The nice thing about OpenMP is that it's portable, meaning that you can write your source code on, say, for example, Linux and run it in Windows or running on Mac and so on. And so it's a standardized way of doing this sort of shared memory parallelization. Now, there is another thing called pthreads, which is another standardized shared memory parallelization system, and that one is more to do. That one it's at a lower level of abstraction. It gives you more detailed control, but it also means that it's harder to use because it gives you greater detail control. And so OpenMP then instead lets you have a higher level of abstraction, and so you don't have the detail control, but then for standard type of things, it's easier to write. So if you've got a serial program already, to finesse it into OpenMP is much less work than if you had to do it in pthreads. The other thing is that OpenMP pragmas are ignored by the compiler when you compile it as a serial program, and so if you write your programs properly, you can actually just compile it as a serial program and it works exactly. The other thing about OpenMP is that the scoping of thread safe data is simplified versus pthreads. There are certain ways that it will make things simpler. Now, the way that OpenMP does things is that you start out with one thread, and this one thread will then work normally like in a normal C program until it reaches this fork. Okay, there's a fork where it says, okay, I'm going to fork it into a bunch of different threads. So you've got a bunch of threads here, and so you've got the master thread fork and the worker thread forks, and when the worker threads die or suspend at the end of parallel code, it joins back to the master thread, and information is then passed on the master thread. The master thread continues until it forks again, and so on. So the simplest parallelization and the most common parallelization found in OpenMP is when you have a for loop. And if you have a for loop that is an integer for loop, then OpenMP makes the parallelization really easy. This is when it has what it calls a canonical shape for OpenMP to parallelize. So for a loop to have a canonical shape, it means that you can just say, I want this parallelized, then it will, the OpenMP will deal with it, and you don't have to deal with it, how to get it parallelized. So one of the things about this is that it must not have any premature exits from the loop, because if it has premature exits from the loop, like break, return, exit, or go to statements, then it cannot parallelize it. So here's how it goes. Oh, you can't see my pointer. Oh dear. I thought you could see my pointer, but it looks like you can't. Okay, so I have to tell you exactly where it is that I'm referring to. Okay, parallel for pragma is this. This is the this pragma OMP parallel 4. This is that special compiler directive that tells OpenMP, look, I'm going to turn this loop into a parallel program, and these pragmas then tell the compiler, look, optimize it for this kind of thing. And the master thread then will create a bunch of new threads when it hits this pragma OMP parallel 4. And with each one will have a separate execution context. That means that those local variables and memory will be unique for each thread. But then there are things that are outside the parallel pragma, those variables that were declared outside the parallel pragma, they are shared by default, except for that loop index, which in this case is the loop index I. So how many threads will OpenMP create? Remember I said earlier that there was this thing called environment variables here. Earlier I said about these environment variables, and you might be wondering what it was, and here is where we see the environment variable. OMP num threads. This environment variable will tell OpenMP this is the maximum number of threads you want it to use. Well, what if we wanted to parallelize the outer loop as well as the inner loop? Then if I put a parallel for pragma above the outer loop, then what happens is that J will be because J was declared outside the loop, it will be shared, and then each instance of each parallel of I running the J's will get clobbered. They will get messed up because everybody's sharing the same J. So that's the problem in this particular situation. So OpenMP has a way to deal with that, which is private variables, where it's telling it, look, I need a separate one of these variables for each thread that's running this. So what you do is you say private J in this case. So we have this private clause, we add it to the pragma OMP parallel 4, and it says private J. And so now it will not go all the way. It will have it will have a separate J for each of these independent I loops. Okay, because remember pragma OMP parallel 4 is coming at the 4i. Okay, so since the 4i, that means that there'll be multiple i's running at the same time on different threads. And if we had the loop like this, then the j would be shared, right? If the j is shared, then it would clobber each other. Each I would be clobbering the j separately and messing up everything. So by having the pragma OMP parallel 4 with private j, then we're telling it that, oh, I need a separate j for each one of these i's. Okay, make sure that you give me a separate j so that when I have a for j equals 0 to width, for I equals 0, it will be a different j from when I equals 1. So that because I equals 0 and I equals 1 may be running in parallel, you cannot have the one from I equals 0 clobbering the j from I equals 1. You'll mess it up. So that's why you're telling it, I need a private j for each one of these i's. So the value of j is then undefined at the start and exit of the loop, because when you just say private, then you just make a new j for each one, and it's just whatever happens to be in memory at the time. But it's okay for this case because first thing we do is we initialize j equals 0. So the fact that j is undefined is no problem here. So private variables are not initialized. See, so they start with any whatever happened to be in memory at the time, and so you're often just stack variables on the program stack. If you remember back to your undergraduate days when you learned compiler construction or compiler design, or that whole subject that where it taught you how to construct a compiler, well, that's, and you remember if that the memory is put on the stack, right? When you call a function, the memory is put on a stack. So that's what happens here, that this is probably implemented in most cases as just a stack, an automatic variable on the stack for each thread. And so whatever happens to be in that memory location, that's what it is. So for example, this code here, it says I equals 10, pragma OMP parallel private I, and then I say thread %d, I equals %d, and then I get the thread number, and I print the I. Then I say I equals 1000 plus OMP get thread num, and then I print the I at the end there. What you end up with is just random numbers. It's like you run it the first time, you could get 0, 32717, 32717, and 1, and then I is still 10, the original 10, not changed. And then the second time you run it, it's totally different numbers. It's just random, because we did not initialize inside the parallel region, and so anything that we do there will start out with a random number, and after it ends, it does not bring back that number to the outside of that loop. So I, which was starting at 10, remains at 10. It doesn't change. Okay, so you see, in both cases, I is 10, and it doesn't change. Well, that brings up the point. What if I want that I equals 10 to go into this loop? You know, I want that I equals 10 to come in which case you need to do this first private special thing. Okay, first private. So first private says that I'm going to do this initial values copied from the master thread, and last private means that I'm going to have the last value copied out back into the master thread. So here's an example. If I change the code to say first private and I run this, then it will make sure that I copy the value 10 into this thread, and then it would always say I equals 10. But because I didn't say last private, so when I finish running, I is still 10. It hasn't changed. Okay, so first private and last private are just special cases of private, and most of the time you don't need it, because it's like that for loop I showed you earlier. But occasionally it does need it, so that's when you use it, when you need it. There's this interesting use of C++ objects as automatic first private variables. They'll be initialized through the copy construction, if you remember from your object-oriented studies in your undergraduate, that the copy construction will initialize it once and destroy it after the block, and so you don't need to do the number of threads in advance, and as many copies will be created as needed. So that's in C++, but in C, you will need to use this first private. Okay, so I'm going to now explain to you demonstrate to you this using of the private. Now here's one where I don't use private. So it first says I is 10, right? And my pragma OMP parallel 4 is on J, all right, on the loop for J. So this I is going to be the shared I of everybody. So I'm going to print J and the thread number and I. And I put my max 16, and it so happens that this particular PC has 16 processors. So it should have enough threads for one thread to do each loop item. So let's run that. First we GCC that thing, and then we run it, and you see that in fact, as I said, I've got 16 threads, so I've got exactly one thread per loop variable. And you see, wait a minute, at the end of it, I is 1013. And why is that? Why is I 1013? Because it just so happens that the last thread to run was 13. So if I run it again, it's now 1010 because the last thread that happened to run is thread 10. If I run it again, it's 1002 because the last thread that happened to run is thread 2. So you see, you get inconsistent results because I is shared. So whoever happens to be the last one to run, that's the one that's going to be it. So what are we going to do about that? Well, okay, so let's edit the file and we say, okay, well, actually, what we want is I to be private. Okay, so we have private I. Private I, yeah. So now we compile it again, and we run it again, and we say, oops, that's not run, that's edit. Run it again, and we go, wait a minute, why, how come my I is now always 0? I thought I initialized it to 10. And that's because when it's private, it just makes a new I. And in this particular case, the new I started out at 0, just the way that the compiler did this thing. So we still don't have our correct I. It's just it's whatever happens to be there in the memory at the time. And furthermore, my I out here comes back as 10, which if you look back at the program, it started out as 10, it ends at 10. And like, what happened to my I? Isn't it supposed to add the number of j? Because after all these loops, the thread number should be j, right? But no, it's not, because we are doing private I, which means that the I exists from here to here, and after this we go back to the outer I. So the inside I, the private I, is different from the I out here. So this I out here never gets changed. It's always 10. It stays 10, and so at the end of it, it's still 10. So okay, so we've got two problems here. One is that I doesn't get copied in, and it doesn't get copied out. Okay, well, let's deal with it doesn't get copied in. So we have to do first private. Okay, so we said first private. So, and now we compile it and we run it. And yes, I is always 10 now. Good. But at the end of it, it didn't add the I. It should have added 15 to the I. I should have added 1000 plus 15, so I should have been 1015. So that's where we have to have the last private. So we add last private I. And now we compile it again, and we run it again. And finally, it all works. It starts out as 10, it ends up as 1015. Yes. Okay? So that's how just to show you again, that's the program. See, you have the first private and the last private there. So you've got this first private, which brings in the I from outside, and you've got the last private, which then says, well, the last effective loop thing, do that one, and that's the I that we got. Okay, now there's this schedule clause which helps. You can make things more tuned by telling OMP how to handle the parallelism. And you can have static, which is iterations divided into size chunks, is specified and statically assigned to threads, and dynamic, where iterations are divided into size chunks, is specified and dynamically scheduled among threads. So and then there's general parallelism. You can say that this entire block of code is to be executed in parallel, and you use pragma OMP parallel before a single line or block of code enclosed by curly braces. Then you can have all threads, including master thread, executing everything in the block. And the reason you might do this is because if you fork and join and fork and join, there's certain overhead in setting the parallel chunks. So, and so that's why you might want to do that. Okay, so I'm going to do a example to explain some of the things we talked about just now. This here you see I have a parallel section here, okay, and then I have a non-parallel section here, and then I have another parallel section here. So I set this to 4 processes, and so I put also the loop to be 4. Then you'll see that each one of these loop variables will go in 4. So here we run it, and you see so this is the first parallel section, and then the single middle section, and the second parallel section. So what happens is that when it opens this first parallel section here, it will incur some overhead to open it, and then when it closes it, it'll incur some overhead to close it, and then it does this, and then again it opens it and incurs some overhead and closes it again. So if you don't want that overhead to be incurred twice, what you can do is you can have it run the whole thing as one parallel section. So we can put in here pragma or OMP parallel. Then because we have many lines, so we put the open and close. Then this one we don't say parallel again because it's already parallel, so we just say 4 and we say 4 here. So what happens is that now the whole parallel section goes all the way from here to here. Let's redo the indentation so that it will be clear. Okay, so we have this here, and then this is inside this whole thing. So this whole thing is parallel, one shot parallel. Okay, so we have this middle section that will be then run in parallel also. So you see 4 threads running this instead of 1 like last time. So you see, first it has the first section, then it has this middle section is run in by 4 threads, and you see it's all mixed up because what happens is that thread 0 ran it and then he went straight to the second loop. Meanwhile, thread 3 is running this and going to the second loop. So if you don't want this messiness, what you can do is you can put a barrier, just like, remember MPI barrier? Well, OpenMP also has a barrier. So pragma OMP barrier. Okay, so that will not be messy. It will stop here, everybody synchronize before continuing. So like this, run it again, and you see now it's nice and neat. The middle section is in the middle, and then the second loop starts. Okay, then there's this atomic directive. So what happens, why we need this is that, you know, like when you have some shared variable that you're updating, like for example here, I have an I, and then I have this I, and oh, now my pointer is back. I wonder why it disappeared last time. I have no idea. Anyway, so anyway, I have this I here that I initialize to 0, right? Then I add 1 to I. The thing is that it could get clobbered, because if what is add 1 to I is load the value of I, add 1, and put back into I, right? So it's possible, if you got threads happening at the same time, that it loads the value of I, let's say it's 4, and then it adds 1, so it's 5, but meanwhile somebody else has loaded the value of I, which is 4, and then it adds 1 again. So instead of getting 6, you get 5, because 2 of them added at the same time. So what you do is you have this pragma OMP atomic to make sure that only one process can do this command at a time. So that's how you can do that. There's also a single directive where if you have something that's not thread safe, for example, a GUI or I/O operation, then you can tell it to put a single directive that says only one thread should do this. The other threads will wait at the end of the block, and to finish, then only they go on. So that's the single directive. So there are many other resources. I mean, this is only touching a small part of OpenMP. So when we get to the OpenMP tutorial, you will see a lot more stuff. Okay? Well, you'll see some more stuff, but that you can go online and find out a lot more stuff about OpenMP.